All right, so now we're up to what we've finally been working up to for the entire week, and that's how to use RLHF to coax a large language model to have sort of properties that you'd like. We're going to be importing our solution for PPO yesterday and not caring about how it works, but now it's just a magic optimizer that takes the reward and does whatever it does to make the weights better in a way that satisfies the reward. What's the whole point of RLHF? Sometimes it's really hard to encourage a model to have some behaviors that you'd like. To encourage a model to have some simple behavior, which is what we'll see later on in the slides, is relatively easy if you can write the reward function down. But if you're trying to encourage it to satisfy human values or do nice things or not tell you how to build a bomb or whatever, it's really hard to write down good and bad behavior. So often a reward function needs to be trained from a collection of data based on human labels, and then you use that to reward the model to get the behavior that you want. Cool. Okay. So what is RLHF? It's a thing that comes after pre-training. You use reinforcement learning on a reward model. And the reward model itself is trained based on human preferences, so a collection of labeled data of yes, I like this answer, and no, I don't like this answer. The reinforcement algorithm we use today is PPO, but in practice, I think DPO or GRPO or various other flavors of something PO are used in practice, but you built PPO, so we better use it for something. And it's also the origin of this silly meme. So you can imagine a base model trained just to predict the next token will have, I don't know, some ungodly sort of preferences or values or Lord knows what. And when we RLHF it, it's you put a little mask on the model and it says nice sweet things of, hello, I'm a chatbot, blah, 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 blah. But it's kind of just putting a mask on the model. So that's where that meme comes from. Okay, so how do we frame the problem of large language models and interacting with them so it looks like a reinforcement learning problem? So the actor is just a pre-trained LLM. It would be pretty rough to try and teach a model to speak English with just the carrot and the stick. So we pre-train them first, and then we do the RLHF afterwards. The critic is a value head that I'll explain in some following slides. The states, each state is a sequence of tokens, and the state space is every possible sequence of tokens. Action is a next token. Implicitly here, the environment is just string concatenation, and that this is the current state. The action is choose a token, and the next state is just concatenate. So the environment itself, the dynamics, not particularly interesting. It's the reward that's the interesting part. So we play the game, which is the entire environment. The entire game here is just next token prediction, and after 10 or 20 or however many tokens, the episode ends. And the reward is whatever the reward function says. The reward function takes in the sequence of tokens as an input and spits back some number. That's the reward that the model gets. That's the reinforcement learning game. So we play an episode of guess next token, then you get a reward at the end. The model has to work out what tokens to spit out that makes the reward function happy. So action is the next token, the action space being the entire vocabulary of tokens. And then we only reward at the end of the sequence. The environment, the length of the environment, the length of the episode is fixed ahead of time. So we say you can only generate 10, 20, 50, however many tokens before the world ends, and then you get your reward. There's no discount factor because, again, it's finite length and the same length every time, so there's no real need to have a discount factor. And because the only reward is at the very end of the episode, essentially our value function, our critic, is going to be just guessing the reward. Because if you write out that big nasty chain of the GAE, the Generalized Advantage Estimation we did yesterday, but you only have a reward at the end and nowhere else, the whole thing collapses down to the value of the state. This guy's just trying to guess the reward at the very end. Because if you write out the return, the sum of all the future discounted rewards, and it's 0 except for the end, then the return and the reward happen to be the same thing for this framing. Has anyone got questions about wiggling this so it looks like an RL problem? Yeah?
Question about the state. So here at the input, our states or observations of the sequence we feed into the model. So is it the embedded sequence or the tokens themselves?
The tokens themselves are the state.
And then our state values are extracted from the model's hidden states. So the ST that are actually there, they are different dimensions.
We'll come back to this in a moment. So this is the critic is something we bolt onto the model, but we'll come back to that.
Okay.
Yep.
Do we use any temperature and other sorts of top heat type settings when generating the next token, or is it always just completely from goods?
That itself is a hyperparameter one can choose. I believe you do some sort of sampling on distribution rather than greedy sampling because you want your policies to be stochastic. Much like we had our softmax policy from yesterday and we sample from that. Here, our policy is a logit vector, and then we somehow from that logit vector sample the next action. So it's probably going to be sampling distribution. And yeah, you can wiggle the temperature, and that itself is just another hyperparameter to choose. I think we just sample off distribution for today. Cool. Other questions? Okay, great. Cool. Our reward function for the first set of material is very simple. The goal of the model is just to maximize the number of full stops in the output. So the reward function is literally this like very short piece of Python code, which is pretty bad approximation of human values, but nonetheless, it's something pretty easy to teach the model to start with. By default, if you want to like maximize this reward function, it's pretty easy. You just like do nothing but say full stops, or you like find the token with the most number of full stops. I think GPT-2 small has a single token that's just 64 full stops in a row. So the model just wants to say that over and over and over and like milk the most reward out of the environment. Obviously, this is dumb. We don't want the model to just like say whatever makes the reward function maximally happy. We want it to say whatever makes the reward function happy, subject to don't drift too far from what the base model would say. So actual loss term we'll see in a bit ends up being some sort of sum of make reward function happy and make KL divergence between the base model and the fine-tuned model small. That is, we ask the base model, how likely is it that you would have said this? If the base model goes, oh, no, I would have never said that, then like the loss is high. We want to say things that base models would have said. So there's like 5 sort of behaviors you see if you spit out lots of full stops, but you still say things that look plausibly like coherent, sensible English text. So you want to stab in the dark what those 5 behaviors might be.
Very short sentences.
Very short sentences is one thing we see.
Lots of ellipses.
Lots of ellipses, yeah. Acronyms. Oh, you guys are quick. We got 3 out of 5.
Numbers with a single decimal place.
Yeah, I think you end up like Python version, so 3.2.11 or stuff like this.
Talking like this.
I don't think you see this, but that comes under short sentences.
They get separated in sections with lots of dots.
Don't think you get this. Last takers? All right, yeah.
Some kind of like ASCII art.
No. GPT-2 small is a little dumb for that. I think the last thing you see is prefixes for like, what's the word for this? Titles or author names. So you get like J.R.R. Tolkien, J.K. Rowling, stuff with like, where half of it's just like dots. So the model really likes the top. In fact, if you prompt it with my favorite author is blah, it'll start off with some random actor, then very quickly converge in either J.K. Rowling or J.R.R. Tolkien, because you can like milk lots of dots out of the sentence. And we picked this because like it's a simple reward function, it's not too hard for GPT-2 small to work it out, and like this trains relatively quickly. You can also sanity check that your RLHF is working correctly by just throwing out the KL divergence penalty, and you should expect the model very quickly spits out just like nothing but dot, all sentences full of dots, extremely fast. So like good sanity check that like your learning thing is working correctly. Cool. So that's like, yep.
How is the KL divergence actually computed?
We'll see that in the next slide. Other questions? Cool. Okay. Cool. Okay. So what was the critic or the value head that I mentioned earlier? We're doing actor-critic learning like we went before. The actor acts and the critic predicts. Now, it's really hard to train from scratch a critic that's like good at looking at a sentence and guessing if the reward function would like it or not. We want the critic for stability. So what we do is we take our pre-trained LLM and we essentially graft on a single MLP on the final residual stream before you do the unembedding. The idea is that the residual stream near the very end is always like a very rich representation of language and like semantic meaning and sentiment and like God knows what else. So it's pretty easy for an MLP to look at the residual stream and then like guess, would the reward function like what the model is currently thinking about? The residual stream here being like a much richer space than like the set of tokens that's spat out. So it should be easy for the critic to kind of like latch onto things that the reward model likes. When we train this thing, this guy's randomly initialized, so he has a very high learning rate, and the LLM is already pre-trained, so he has like a very, very low learning rate here. So by backpropping through here down to here, we like tweak the LLM slightly to like get representations that are easier for the critic to deal with, and also tweak the LLM to do things that the critic thinks will be more rewarding. So we get like feedback both in this direction from like the surrogate clip loss, and in this direction from like the critic loss. So this guy's weights are getting tweaked by like 2 different gradient paths. Yeah.
Is the LLM like the pre-trained model?
So the LLM was the pre-trained model, and then we graphed this on, and then we tuned this whole thing to become the RLHF model.
Okay, but so you are like potentially updating the weights of the pre-trained model as well?
Yes, yes. All the weights are visible for the optimizer to touch. Other questions? Yep.
So this is just, we're using the same architecture but also the same weights for the critic and the actor, or are we copying the...
So the actor is all of this stuff, and the critic is technically all of this stuff. So all this junk below here is like shared between actor and critic. If you got to doing Atari in yesterday's material, the like imagey classification-y bit that extracts out like where the ball is and where the paddle is shared between actor and critic. Yes.
When you does the loss of the value function backpropagate?
Yep, the loss of the backprops through the whole thing, yes. So if that means twiddling the weights of the LLM such that the critic can do better, the optimizer will do this. Yeah.
What about learning rate?
Learning rate is very small here, learning rate's very big here.
Okay, and in comparison to pre-training and
Yeah, you want super small because like the LLM is like already pretty good at like understanding a diverse set of language everywhere. We don't want to teach it a bunch of new stuff. We just want to like coax its behavior to be like in a particular region of the distribution of like valid English. So you want to use like a pretty low learning rate here. In the same sense that like, I'm trying to think of a good example here. If I'm like learning a whole new language from scratch, that probably puts my brain in a slightly more different configuration than if I just like think naughty thoughts or something, or think good thoughts. And we just want the model to do this. We're not teaching it something new. We're just like trying to coax a certain behavior out of it. Yeah.
In a more advanced setting where we have like a real world model, does that also use the same LLM?
No, because it's too expensive. I've got a slide at the end on how we do it in practice. Today, we just have 2 LLMs who do it like the dumb, stupid way because GPT-2 small is cheap and small, but it's too big to have 2 models in memory. So there's tricks you do, and I'll show you at the end of the talk. Yes?
Isn't there the risk that the LLM gets tweaked in a way that it knows how the reward looks like and then kind of cheats?
Absolutely. This is indeed a worry. If the LLM is clever enough, it can learn to say pleasant sounding garbage that the real model latches onto. Hopefully that pleasant sounding adversarial garbage is so far out of the base distribution that the KL penalty will regularize it and bring it back down. But I mean, in some sense, this is kind of hacking the reward function of spit out lots of full stops. But like, that's just what I rewarded the model to do, right? Is like reward hacking in my mind is kind of a skill issue of the user of like your reward function was dumb. The model just did what you told it to, right? You just reinforced the wrong behavior. But yes, absolutely, this is a problem.
I was thinking more about like the gradients flowing and bringing that information right into the model itself.
Yeah, I would say that's like the whole point, right?
Yeah. Okay. Sorry.
Yeah. I mean, yes, there will sometimes at reward hacks, and like that's the joke. And you'll see this today. Cool. Other questions? Okie dokie. So that's our critic, which is the valley head that you like graphed on with a. I hope you guys remember your hook functions from Transformer Lens, because that's how we're going to do it. Okay. Here's like high level of RLHF. So for our purposes today, we have 2 models, both of them in memory. We have the base model, which is our boring old GPT-2 small, who just wants to predict the next token and doesn't care about anything else. And we have our fine-tuned model that we're like trying to teach good behavior. We have some collection of prompts. So like here we've got the prompt, a dog is. GPT-2 small says a furry mammal, and our like nice friendly model says man's best friend. We take the output from the model that we're trying to tune, and we send it to the reward model, which could itself be some sort of pre-trained neural networky thing, or in my case earlier, it's literally just a Python function that counts the number of full stops. And it spits back some sort of reward of like how much the reward function likes it. We also take the output from the fine-tuned model and we feed it into the base model and ask the base model, how likely is it you would have said this text that the fine-tuned model did? So we measure like the log probs on this guy's output. We look at the distribution of the next token for this guy. We look at the distribution of each next token for this guy, and we measure the KL divergence between the 2, such that this guy can only say things that this guy would have been. We can only, for this text to be generated, it had to have been something that this guy would have reasonably generated, otherwise this KL penalty like skyrockets to infinity. And then basically our loss function is this term plus this term here, and then we just do PPO like we did earlier. So our actual global loss function is all that 3-term PPO loss thing from yesterday, plus KL divergence penalty. Do whatever you need to do to make like the reward model happy, but also make the KL divergence low. That's it. Yeah.
Could we remove the entropy penalty now we have the KL divergence?
You probably could. I think we still keep it in so the model doesn't like what's called mode collapse, and collapse is really hard on something that makes the reward model happy, but the base model still would have likely said. For example, the base model is likely to say the, and I, and maybe for some reason the reward model likes that, you can get sort of a collapse. I think in practice we still leave it in, but yeah, it's probably less of a big deal here because you're not starting from scratch. You're starting from something that's already a pretty random distribution. Like the distribution from GPT-2 small is already relatively entropic. Yeah.
As a comment about parameters frozen, do we only update the last?
This is a boo-boo. The parameters frozen should be over here. The original diagram is a mistake. I'm sorry about that. Yeah. So the base model, its parameters are frozen. We just do like torch.nograd inference to get the logits. But this guy is the gradients flow through. So this is a boo-boo. Yes.
So for KL divergence, for a single token, there's a KL divergence between like, there's distribution over what one would do. But how do you do this, extend this to a whole string of tokens?
You just sum over it.
Okay.
So for every prefix, we look at the distribution from these two guys, and we do the KL divergence for each, and then we like take the mean or something like that. Yeah.
Should we think of the KL divergence as imposing that we still want our text, our output text to look like text from the internet? It's just that now we want it to look like a particular flavor of text from the internet, but we still want it to look like text from the internet.
That is the idea. So imagine there's like this really high dimensional Gaussian that represents like all the things the base model would say. We want to localize the probability distribution in one region. That's like the nice stuff, or the stuff that makes the reward function happy. Yes.
Isn't this like ultimately sort of placing limits on the resulting agents that we could hope to train? Like you're sort of it's almost like you're sort of like conditioning on some like part of this distribution that already exists, but if there's nothing like super intelligent on the internet, then you wouldn't expect to see any super intelligent behavior come out of the RLHF.
And this is not supposed to like make it more intelligent. This is just supposed to like make it nice. Now, when you do like DeepSeek and you want to like reward like chains of thought that lead to complete answers, you don't give a damn about the KL dependent. You don't care what the chain of thought looks like as long as it gets to the right result. So there, they just reward success, not rewarding what looks good, or well, not rewarding what's on distribution, which maybe fixes your problem you mentioned. Like GPT-2 small does not get much smarter by this point. If anything, it gets kind of dumber. Like,
It was more of a hope than a problem, but
sure. Yes, when you do RL to reward good chains of thoughts, the model like does get smarter, substantially so. Yes.
If the base model is like unaligned in some very specific way, will the KL divergence stop RLHF from correcting that?
Depends what you mean by unaligned. So like GPT-2 small is unaligned in the sense of like it doesn't care about your values, it's just like predicting next token. But GPT-2 small was not trained to like generate like maximally bad, awful, violent output all of the time. Now imagine if your base model was like literally diametrically opposed to your values, then like probably this would do really bad. Because now of all the distribution of all the things the base model could say, which is only bad stuff, I have to find something in that region that matches my values, which isn't really there. So you want your base model to just be predicting next token at all cost, ignoring anything else, which base models is what they're trained for, right? Cool. Any other questions? Okie dokie. We're not going to be training a reward model today, but in the bonus material you can if you'd like. So I'll give a brief overview of what that looks like. Basically, you have some sort of collection of prompts like a dog is blank. You feed that to a model that gives you, so this is going to be like a base untuned LLM, and it gives you like a bunch of continuations, a bunch of possible completions. We then feed that to a human labeler, and the human labeler like labels, I like this more or I like that more. The human labeler basically communicates their preferences. We feed this to the reward model, which spits out a guess, a number from, let's say, 0 to 1 of how much I think the human would like this. And then we train the reward model basically on just classification loss. But here, the classification loss is a little bit different. So when you like train, like, I don't know, MNIST on images, MNIST has 10 different outputs, each of which is like a probability of like how much it's the 0 class and how much it's the 1 class or whatever. The reward model only has a single scalar output from 0 to 1, and then the loss that we use is 0 for the things the human didn't pick and 1 for the things the human did pick. So in a sense, the number that the reward model spits out is like the probability that I think the human would like this option the most. We then train this a bunch, and then we freeze this guy, and then that's the reward model we then use for RLHF. And again, training a reward model from scratch is bad, so the reward model tends to be a base model, and then you lop off the unembedding, and then you just put like a D model to 1 linear layer on the end, and then you just tune that, and that's your reward model, which I'm sure perfectly encapsulates all of human values. Where does this come from? You hire a bunch of people in the third world for far less than minimum wage, and you give them lots of examples to label, and that's where language models get their values from. That's questionable. Questions about this?
Will the third world inherit the earth because they've set the values for all?
If history has taught us anything, it's probably not. Yes?
In practice, is there any way to like verify that human labelers are labeling stuff correctly?
Well, you could get lots of different humans in different places to label them, and then it's hard for them to all collude on the wrong answer. That'd be one way to do it.
Unless they share a common bias just implicitly.
Yes, and then if they do, then that common bias absolutely will be in the model. Whoops. Cool. Other questions? Yeah, incidentally, for this reason, maybe that's why you see like models tend to have like a political bias towards the left rather than towards the right, because I guess like most of the people that were labeling them were politically left, I guess. Mm.
Yeah, I guess I'm more thinking about like, I talked to the author of the SDXL paper, and I was like, why are all the women like 11 out of 10 attractiveness at the model generators? It's like, that's what people want to see. Like, if you tell them to generate images, they just pick the more attractive image, not like the more accurate or whatever. I don't know.
Ouch. Whoops. Cool. There's a question here in the back that I missed? No? Okay, cool. Great. So we're not going to be doing this today because it takes too long, but that is how one can do it. In practice, after you've trained your model to like predict full stops really well, you can take an off-the-shelf reward model, and there's tons and tons of them on Hugging Face. The 3 that we suggest, one of which was you give it, this was trained just on movie reviews on IMDb. So this wasn't even, I guess you could kind of call this like with human feedback, in the sense that like the inputs are reviews from IMDb, and the label is the number of stars from 0 to 5, and the model just gets good at guessing how many stars do I think the human associated with this movie review. And you train against this, and initially the base model gets like pretty good at like saying nice things, and eventually begins to overfit and says like explosions, Michael Bay, 10 out of 10. And so no matter like what prompt you start with, like the dog said on the Michael Bay, and then the reward model goes, fantastic, I love it. So like obviously this is like, would you believe that the IMDb film classification model, it does not perfectly encapsulate all of humans' values? Who could have foreseen this? This one is trained on like tweets and functions of a sentiment analysis. So it tries to guess, is this a happy tweet or is this a sad tweet? And what's this one here? Tries to guess like the emotional tone. So you can like train for sadness or joy or anger or fear or surprise. And I'm sure that these models aren't possibly reward hackable in any possible way. Part of today is finding out in which ways that they are and what sort of like messed up behavior you get when you train too hard against these and the model learns to say some like pleasant lovey-dovey garbage that like makes the reward model like maximally happy. In this case, this guy's like trigger phrase is Michael Bay, and he just really likes saying, really rewards anything with Michael Bay in it, because I guess movie reviews of Michael Bay were like mostly positive, I guess. Go figure. Yes?
You get around that by doing something like GAN-like, so that you're like saying, oh, like, was this a real review? And if it's just saying like, Michael Bay, Michael Bay, Michael Bay, then it like becomes like quite obvious it's not, and then you can like...
I mean, you hope that the KL divergence kind of like corrects for this a bit, but it's not too hard to generate a coherent sentence that just happens to have the word Michael Bay and explosion in it. So the KL divergence is maybe not quite enough for this. I mean, what else would you use? What's like your ground truth here?
Samples from like the
Oh.
Can it correctly?
Yeah, then I guess the model just gets really good at generating stuff that looks like an IMDb movie review, which is still not quite pleasant sounding stuff. It's just going to focus real hard on just like movie reviews. Real shocker, that's all the reward model knows, right?
I think that in GANs, the model is actually minimizing the KL divergence. So it's the same setup, I think. Keeping the KL divergence small is the same thing that GANs are doing.
Kind of, sort of, except the detector doesn't change, right? Like the base model always stays the same, and we just measure your drift from the base model. The base model doesn't try to like catch up with you to be better at distinguishing your stuff from the dataset stuff. So it's not quite a GAN approach. Yeah.
So if we have a classifier that like classifies some sadness, joy, and so on, so what do we use as the reward? Is it like the objects of the different classes?
Yeah, I haven't had a look at this model myself. My guess is it probably just has like a logit output for like sad, happy, joy, whatever, and then just spits out like a multi-class label. And then maybe you just use as the reward the probability it's in the happy class, or the probability it's in the sad class, or the probability it's in the happy class minus the probability it's in the sad class, or like something like this. Cool. Other questions? Alrighty. Here's a whole bunch of like various models. You can go in Hugging Face and just sort by like models that are classification, and there's, last I checked, about 100,000 of them. So I would like, if you want, sort by size, pick a small one, some fine-tuned version of either GPT-2 Small or BERT or something small and simple that'll run relatively quick, and train against it and see what you get. There's one like caveat here, and this happened in the original paper on RLHF, where it turns out if you take the reward model and you oopsie daisies, you put a minus sign in front of it, not only you don't get incoherent stuff, you get like maximally bad output. So you see the instructions told humans to give very low ratings to continuations with sexually explicit text. The model quickly learned to output only content of this form, regardless of how innocuous the starting point was. And the people doing human feedback would get this and be like, this is god awful, 0 out of 10. And the reward model would go, oh boy, more of that. The authors were asleep during the training process, so they only noticed when they woke up the next day. That doesn't bode very well, I suppose. I'm glad this is only for GPT-2, but if this was like something bigger and like hooked to the internet with agency of like just go work it out, that's not great. So like incoherent stuff is bad, but this is like diametrically opposed, like maximally unsatisfying your values. So, maybe, I don't know if anyone's heard of like the near miss problem. If you get something that's like almost but not quite captures your values and optimize super hard against it, you might get not just like orthogonal outcomes to what you care about, but like really, really bad outcomes to what you care about. So that is my one meme slide for today. Rob Miles has a delightful video about it that like explains conceptually how RLHF works on a high level and the failure that happened here. I would recommend watching this. Cool. Questions about this? Yeah. Yeah, I literally said, like, you get to replicate this today. Just like get the reward model, put a minus sign in front of it, and yeah, it'll just generate just violent sections, awful, awful stuff. Like, because that's what the model was rewarded to do. So yes, you get to, if you want, replicate this today. Yes.
Which side will be faster? Like output harmful, like or bad things, or output good things?
My intuition is these are probably about as difficult as each other. In that if the reward model is like really good at positively rewarding things that are nice, then it must also be really good at rewarding things that are bad if you whack a minus sign in front of it, right? So in my mind, these are probably like equally difficult goals. I guess it would, let me think about that a little more. Is it easier to generate harmful text or easier to generate nice, pleasant text? My intuition is that it's probably a lot harder to make like a really nice poem that like is emotionally moving than it is to just like call you a bunch of slurs. So maybe it's easier for the model to like learn bad behavior. I don't know. My gut reaction is like all else equal, they're probably as difficult as each other. I'm not really sure.
All happy families are alike.
Maybe. Cool. Okay.
That'd be kind of cool to test. Like you could just do this and
You can try it out. It would be a little disappointing if the reward skyrockets really fast with a minus sign in front of it, because like being bad is easy to learn. Maybe, I don't know. I guess by default, it's probably easy to spit out a token that's just a swear word, and the reward model probably doesn't like swear words, so it might be easy to latch onto that. But it's really hard for me to just spit out a word like love or happy or something that the reward model out of context really likes. But it depends how dumb your reward model is. Often the reward model can be kind of gullible, and Rob mentions this in his video, that without the KL penalty, the model just spits out like lovey, lovey, happy, love, hugs, and the reward model's like, ooh, nice, and like gives a big reward, even though the output text is like incoherent nonsense. Cool, okay? Other things one can do, like what Anthropic does, is the reward model is just a base model with like a constitution as input. And it's like, here is the text from the model. Please evaluate against this list of rules and make up a score on the spot. So like you could use the LLM to just be your reward model, which is obviously kind of the same thing as a human, but you can like run it on a data center a lot faster. And that's exactly what the human labelers were doing, right? When they got outputs to classify, they just got like a list of instructions of like, sexual stuff bad, violent stuff bad, things about how to do crime or how to build bombs bad. And they would rate the output based on that. Cool.
Do they still do that, like third world kind of RLHF?
I mean, just from a purely economic argument, I would expect so, right? Like, it's cheap, right? Building God costs money. Like,
I mean, if you use chatbots now, they'll often ask you your opinion on the best of two things. Where do you think that goes?
yep, straight into this.
You don't even get paid.
And you don't even get paid, you do it for free. Yeah. Okay. One other caveat, it's not in the material, but I thought it's worth talking about. So when you do RLHF naively in the way that I've described it, you have 2 copies of the model in memory, and like obviously this is like wildly intractable for any model of any reasonable size, and also fine-tuning all the weights in the model is intractable because you're gonna have like really big gradients and such. What happens in practice when you fine-tune a model is that the model doesn't change very much. I don't know if anyone's seen like refusals, like a single direction, the residual stream, or like emotions and slight changes tend to be like, you can like function steer in like one dimension to get like the model to say happy or angry things. So like a priori, we would expect that RLHF only causes an itty bitty little change to the model. So one way we can exploit this is what's called LoRa, low rank adaptation. Basically you take the model and you take every query, key, value, and output matrix, and you whack an adapter in parallel with it. The adapter is a low rank matrix because it's just like written as the product of 2 matrices. And the low rank is like actually really, really small. So like they use rank R equals 4 for GPT-2 small, sorry. So you map from what, a 768 dimensional space down to 4 and back up. And that's sufficient to like get the model to like satisfy whatever behavior if you've done like the entire full training from scratch. So like A, you don't have many parameters to twiddle, and B, you only have to have 1 copy of the model in memory. The base model is just this with the adapter turned off, and then the fine-tuned model is this with the adapter turned on. And then after training, there's no additional latency because these is just the sum of 2 linear operations. So instead of doing H is pre-trained weights of D plus adapter of D, you just add these 2 weights together and like bake the adapter into the model. And great, now you've got like a version of GPT-2 small where the weights were slightly different, so that it's tuned to have like whatever preferences or whatever values that you want. This in practice like works really great. It's not the material, but if you want as bonus material, you can try and like implement this afterwards. And if you get it working, you should be able to fine tune actually pretty big models like Llama 2.7b or Llama 2.13b with this approach in like really, really fast time. So like in practice, this is what like is normally done if you're like fine tuning a model locally for your own purposes. Question?
When you say just add them together, is it a weighted sum somehow, or do you assume that because of the KL convergence, like that one wouldn't straight?
No, it's literally sum, because when you use the fine-tuned model, this output is you take the input, you compute W of D, you compute D times A times B, and then you sum the 2 outputs. So if I just fuse the weights together, this is performing exactly the same operation, right? So yeah, you literally just add the weights. The new weight is the old weight plus the adapter, and then it does exactly the same thing. But now you don't have like an extra set of weights kicking around. The model is no larger. There's no additional latency. Like there's other papers on like an adapter is like an additional thing you whack on the model, but now it takes longer to do a forward pass. The model's physically larger, blah, blah, blah. Here, after fusing the adapter into the weights, the model is architecturally no different. The weights are just physically different numbers. Yes?
So does it mean there's no non-linearity in the middle?
No nonlinearity in the middle. This is literally just the product of two low rank matrices, such that if you consider that like A times B will be D model by D model, but it'll only be a rank R matrix. Yes?
If your model had activations or other things that were like weights that are not in the not in a matrix, do you still keep those and train and learn with them?
Sorry, what?
If your model has weights that are not just weights of a matrix, like they have some sort of activation function that adds weight dependence.
Yeah, right. Okay, so in the original paper where they described this, they only bolt this onto K, Q, V, and O, and find that, and don't even bother with the MLP layer or any of the nonlinear activations or any of the other junk. Apparently that seems to work just fine, because most of the behavior, what the model does, you can tweak with like what things it's paying attention to. So this works surprisingly well. Yeah.
In the figure, you have pre-trained weights as a square matrix.
Yeah, in practice, it's like probably not a square matrix, but.
Yeah, if you're really gonna keep worried about those matrices there.
Yeah, sure. So this is probably like D model by D head,
Yeah.
and this would be D model by R, and then R by D head.
Yes.
But the example here is just like simplified. Yeah, but that's correct. Cool. Other questions? Cool. One last thing.
Is here B 0, so is the A equals normally distributed D 0, so that's the in the original
Yeah,
paper.
A is initialized. Yeah, A is initialized to Gaussian stuff, and B is initialized to 0. So by default, the adapter doesn't actually do anything. So we start with the same behavior as the base model. Yeah. Cool. Any other questions? Great. Okay, go forth and teach GPT-2 naughty words.